Hello friends. So today we are going to discuss the questions from the year 2002 and from the year 2003. From 2002 we are having 4 questions and from 2003 we are having 5 questions. So in totality we are going to discuss these 9 questions. So in the first question, which was asked in the year 2002, and it states that in the ideal double slit experiment, when a glass plate refractive index 1.5 of thickness T is introduced in the path of one of the interfering beams, wavelength lambda, the intensity at the position where the central maxima occurred previously remains unchanged. The minimum thickness of the glass plate is. So in this case, that the important point is that the central maxima is having the same intensity as was without the glass plate as well as with glass plate. So which basically means that there will be no net phase difference, and based on this we have to find out the thickness, minimum thickness of that glass plate. So we are given that we are having a glass plate whose refractive index is given as 1.5. So we can say the refractive index of glass plate is our 1.5 and the wavelength is given as lambda. Wavelength is given as lambda, and the glass plate is introduced only in one path only. So we can say that glass is placed in one path only. And secondly, the important condition is that the central maxima to remain unchanged. Central maxima to remain unchanged. So from here we can draw an important conclusion. That means no net phase difference. No net phase difference. And so based on this, we are going to find our minimum thickness, and based on the net, no net phase difference. Okay. And we already know the basic formula, which states that when the light passes through a medium who is having a refractive index, suppose n, then the optical path length increases by a factor of n, and that results in an extra phase shift. So you can say when light passes through a medium of refractive index n, then the optical path length increases by a factor of n. increases by a factor of n, and the extra phase shift due to glass plate phase shift excuse me please, extra phase shift due to glass plate we can write that as delta phi will be equal to 2 pi by lambda multiplied by n minus 1 and multiplied by t, and we want that the central maxima should be at the same location. We want that the central maxima remain at same location. Therefore, we can say that the phase shift must be a multiple of 2 pi. Phase shift must be a multiple of 2 pi. So which gives the equation that is 2 pi by lambda n minus 1 multiplied by t should be equal to 2 pi multiplied by m. And this 2 pi goes with 2 pi, and this gives the equation. We can say that our n minus 1 into t will be equal to m times lambda, and we want this t to be minimum. So you can say for minimum t, that is our t minimum, the value of m, smallest non-zero value of m, smallest non-zero value of m will be equal to 1. So we can write that our t minimum will be equal to, this comes as lambda upon n minus 1. Refractive index is already given to us, that is 1.5 minus 1, and this comes as lambda divided by 0.5. This gives us that our t minimum will be equal to 2 lambda, and the option A is the correct option. So you can say option A is correct. Option A is correct. We come to the next question, and here it states that two plane mirrors A and B are aligned parallel to each other as shown in the figure. A light ray is incident at an angle 30 degree at a point just inside one end of A. The plane of incident coincides with the plane of the figure. The maximum number of times the ray undergoes reflections, including the first one, before it emerges out is. So we are given a figure, and this figure, this is our incident light, making an angle 30 degree with the vertical. Okay. And the separation between the two mirrors, these are plane mirrors, is given as 0.2 meter, and length of the mirror is given as 2 square root of 3. In this case, we would find out what will be the maximum number of total internal reflection that is going to take place. So in this case, this is, we can just draw one particular thing. So we are given that this is a vertical and we have an incident angle that is our 30, and at this point we can say that suppose it is being reflected in this direction and this is our B and this is A. So in the first reflection we assume that the distance covered on the horizontally is, let us suppose, is given as x. And in case of, you can see, mirror, the angle of incident is equivalent to the angle of reflection. Okay. So the angle of reflection will be also equal to 30 degree, and we already know this width is given as 0.2 meters. So we can write that for plane mirror, plane mirrors angle of incidence is equal to angle of reflection. So angle of incident is, let us suppose, given as I, and angle of refraction is our R. So we can write that our angle I is equal to angle R and is equal to 30 degree. And let us call this point as O, this is our P, and let us call this as Q. So we can say in triangle POQ, we can write our tangent of 30 will be equal to x upon, and this will be, let me write it in a different way. So we can write this as PQ upon PO. PQ is our x, PO is our 0.2. And we substitute the value. Sine tangent of 30 is 1 upon square root of 2, and this will be equal to square root of 3, 1 upon square root of 3. So this gives us that our x will be equal to 0.2 and divided by square root of 3. So it basically means for first reflection, the horizontal distance covered is 0.2 and square root of 3. And we also know that the total distance the ray has to cover from P to B, or we can say from O to A, will be 2 square root of 3. So we can say total horizontal distance to be covered is equal to 2 square root of 3. And we assume that, let us consider that total number of reflections is n. You can see let total number of times the ray is reflected to cover 2 square root of 3 is, let us suppose, given as n. So mathematically we can write that our n multiplied by distance covered in one reflection will be equal to the total distance. So from here we get that our n will be equal to 30. So the correct option will be option number B. So you can say option B is correct. Option B is correct. Next question. It was also asked in the year 2002, and it states that an observer can see through a pinhole the top end of a thin rod of height h placed as shown in the figure. The beaker height is 3h and its radius is h. When the beaker is filled with a liquid up to height 2h, he can see the lower end of the rod. Then the refractive index of the liquid is. So we are given a figure and the person can see the top of the, you can see this thin strip whose height is given as h, and total height of, you can say, the beaker is given as 3h. The second part, this the beaker is filled with the liquid at up to the height of 2h. Under that condition, the person can see the bottom of the lower end of the rod. So we can draw approximately the figure for that. So let us suppose this is our, you can say, beaker, and we have a rod which is somewhere here, and its height is given as h. So this is of h, and the height of the beaker is given as 3h. So in the first instance, the person can see the top of the, you can say, this object. In the second case, when the liquid is filled up the height of 2h, so let us suppose the liquid is filled up to here, so this will be about 2h, and now the person can see the bottom of the this particular strip. So let us, now this is, we can say, more or less related with, we can solve it by using the triangle property, and let us call this as, this is our A, and this point is, let us suppose, our B, and this is our C. Then we have D, and we can just draw a horizontal line here, and this end, this point is our E. Then we have F, let us call this as G, and vertically let us call this as H. And we are also given that the radius is given as h. So by considering a triangle, okay, and the ray of light first will be initially without water and this will be with water. Okay. So let us consider this as our angle of incidence, and we are going to have this will be our so let us consider triangle BEF. This point is our E. This is our B, C, D, H and G, and this is our A. So in triangle BEF, in triangle BEF, we can see that our FE will be equal to BE, okay, because this height FE is our H and this BE will be also H. So this portion is also our H. From we can say that our FE is equal to BE and this H is equal to H. So the triangle BEF is our isosceles triangle. So this is our isosceles triangle. Therefore, we can write that our angle BFE will be equal to angle FBE and each will be equal to 45 degree. And also we have that our AC is parallel to FD. So based on this, we can say that our angle BFE will be equal to, we are going to have BFE will be equal to, let us call this as J. So BFE will be equal to JBC and each will be equal to 45 degree. So we get this angle is our 45 degree, and we can write our Snell's law. As Snell's law, we can say that we have our air and water surface. So we can say at Snell's law, at surface AC, and we can write that our 1 upon the refractive index will be equal to sine of I and divided by sine of R. And we can just find out our sine of I. We can say that sine of I will be equal to, this will be our GH upon GB. So we are going to have this as GH upon GB. GH is our H and GB will be equal to H square, and that will be equal to our 2H square plus 2H square and its square root. So this comes as H upon square root of 5 times h. And h goes away. So this we are left with 1 upon square root of 5. And sine of r is our sine of 45, which will be equal to 1 upon square root of 2. Okay. And now we got the value of sine of I, we get the sine of r, we substitute it, we get the ratio of sine of I upon sine of r. This will be equal to 1 upon square root of 5 divided by 1 upon square root of 2, and this gives us square root of 2 divided by square root of 5, and this is our 1 upon refractive index n. So therefore we can say that a refractive n will be equal to square root of 5 divided by 2. So this is the refractive index of the water. So answer is option number B is the correct option. Option B is correct. Come to the next question. So here we are given that it was asked in the year 2003, and it states that in the figure the light is incident on the thin lens as shown. The radius of curvature of both the surfaces are determine the focal length of the system. So here we are given, you can say, three different you can say mediums. First medium is given to us as mu1, and the medium, which is basically a thin lens, is given as mu2, and then we have a medium which is given as mu3, and we have to find out that what will be the its the focal length of the system. Okay. And the incident, you can say, ray is coming as parallel and from medium, which is having a refractive index mu1. Okay. So therefore we have to find out the focal length of the system, and in this case we have to remember that basically we are having three medias. So this entirely is going to have three medias, and the light enters from a medium with the refractive index mu, lens is having a refractive index mu2, and light exits from the refractive index mu3. So first the refraction is going to take place at the first surface. So this lens is given as thin, so it is going to have two surfaces. So this will be our first surface and this will be our second surface. So we can just draw an approximate figure for that. Okay. So we can say a refraction at first surface. Refraction at first surface. And if we consider only the first surface, the diagram will be something like this. So if this is only the first surface and the ray of light is coming parallel, and let us suppose this is the axis, the other ray of light is coming from the other end, and in the first surface it is obviously going to refract, and suppose this is the normal, so it is going to refract in this direction, something like this, and same at the other end also. So first it is going to form the image somewhere here, and let us call this image as I1, and this is our first surface. So we can just write the equation, and that equation is mu2 upon v, let us call that as v1, the distance of the image, and mu2 is our length, minus mu1 upon u, so this is our mu1, and refractive of is given as our mu3, and this is our mu3, that's a third medium, and this will be equal to mu2 minus mu1 upon r, and object is infinity because of the parallel line, so u will be equal to our minus of infinity. So this gives us that our, you can write that mu2 upon v1 will be equal to mu2 minus mu1 upon r, and from here we can find out our v1. So v1 will be equal to mu2 divided by mu2 minus mu1, and multiply by r. Yeah, so this is our position of the image. Okay, and now we come to the refraction at the second surface. Refraction at second surface, and for the refraction of the second surface, you can say the light goes from mu2 to mu3, and so for the second surface, or now we can combine both the surfaces and we can get an approximate, you can say, figure for that. So we have two surfaces. So for first surface we already found out, so this is our second surface, and once again we are going to have the central line, so initially in the first case we drew that it will be somewhere here, okay, but because the second surface, the ray of light will be culminating somewhere here, and let us suppose this was our I1 and we call this as I2. So this distance is, let us suppose it is our V2. Now we are going to find out what will be our V2. So you can say that our mu3 upon V2 minus mu2 upon V1 will be equal to mu3 minus mu2 upon R. And here we have to remember that the image I1 is going to act as an object for the image I2. So I can say that image I1 will act as object for I2. That's why we write in place of object, we write it as V1. And let us call this as equation number 2 and this as our equation number 1. Yeah, this is equation number 1. Or we can simply substitute it, there is no need for that. We already found out that our mu2 upon V1 is, we are going to replace here. So we get this as mu3 upon V2 will be equal to mu2 upon V1 is our mu2 minus mu1 upon R plus mu3 minus mu2 upon R, and mu2 cancels out, so this comes as mu3 minus mu1 upon R. So we were supposed to only find out focal length of this. So we get that our V2 will be equal to mu3 divided by mu3 minus 1 multiplied by R. So this is the position of the image due to the entire system. Okay. And this V2 and is the final position, or we can say position of the final image. So this is the position of final image, and in the question it is given that the light comes from infinity. So we can say that light comes from infinity, therefore the final image will be our formed at the focal length of the lens. Okay. Therefore we can say that the final image will be formed at focal length of the lens. Focal length of lens. So therefore we get our F is equal to mu3 multiplied by R, and this is mu3 minus mu1. We come to the next question. Okay, here this was also asked in the year 2002, and it states that a point source S emitting light of wavelength 600 nanometer is placed at a very small height h above a flat reflecting surface AB. See the figure. The intensity of the reflected light is 36% of incident intensity. The interference fringes are observed on the screen placed parallel to the reflecting surface at a very large distance d from it. So based on this discussion, we have three, you can say, question on it. And in the first question, it asks that what is the shape of the interference fringes on the screen? In part B, calculate the ratio of minimum to maximum intensities in the interference fringes formed near the point P, shown in the figure. And finally, if the intensity at point P corresponds to maximum, calculate the minimum distance through which the reflecting surface AB should be shifted so that the intensity at P again becomes maximum. So we are given this figure. We have a glass AB and the point source S is kept at height h from the glass, and the screen is just parallel with the glass at a distance of capital D. Okay. And we have to find out more or less everything with respect to this point P, which is just behind the point source. Okay. So in the first part, we are going to find out what will be the shape of the interference fringes on the screen. So let us consider that a coordinate system for all the source as well as its image. So this is our mirror AB, and we have a point source at S at a height h. So let us consider its coordinate will be 0, h and 0. And just the virtual image, let us call that S prime, and its coordinate will be equal to 0, minus h and 0. And the P point, which is just behind the S and its distance is d. So let us consider the coordinate of this P is our d, y and z. Sorry, not d, y, z, because this we have considered x we have taken in this direction and we have taken as y, and the origin is our this point. Okay. And for the sake of convenience, let's do it. It's not a big issue. Okay. And let us observe the screen is played as a distance of, so it is somewhere here. This is point P and it has a distance d. Okay. So we can find out the path length of the source as well as the image. So we can say path length from source and image . One second. Intensity is this. The difference observed on a screen placed parallel to okay. So the path length from source and image. From source and image. So we are going to have two paths, and one will be direct path from S and another will be reflected path from S prime. So we are going to have direct path from S let us call that as R1, which will be equal to our d square plus y minus h square plus z square and its square root. And second one will be the reflected path from S prime let us call that R2, which will be equal to our d square plus y plus z whole square and plus z square and its square root. Now we can easily find out the path difference and phase shift. Path difference and phase shift. So path difference will be our R2 minus R1 path difference is our delta will be equal to our R2 minus R1, and the phase difference, because one of the ray will be the reflection, so that is giving us a phase shift of pi. So you can say that reflection from denser medium introduces a phase shift of pi. Or which can also say a path difference of lambda by 2. Path difference of lambda by 2. So therefore we can say the effective path difference that is our delta effective will be equal to R2 minus R1 plus lambda by 2. Now we have to find out the condition for constructive interference, that is our bright fringe. Condition for constructive interference and our delta effective, that is path difference, should be our integral multiple of lambda, and we can substitute it and we get this as that our R2 minus R1 will be equal to m minus 1 by 2 and multiply by lambda. And we can make you can say approximate analysis of the square root, and for the sake of convenience we say let capital R is equal to d square plus y square plus z square and its square root. And we can use the binomial, you can say approximation. Binomial approximation and this tells us that 1 plus epsilon L is approximately equal to 1 plus epsilon L divided by 2. Okay. Under the condition this epsilon is very much less than 1. Therefore we can write that our R1 is approximately equal to R minus Hy by R, and our R2 is approximately equal to R plus Hy by R. So therefore R2 minus R1 approximately comes as 2hy divided by, this comes as d square plus y square plus z square. Now we can just substitute it, and this will be giving us that our 2hy is equal to, divided by d square, y square and z square, its square root is equal to m plus 1 by 2 and multiply by lambda. And we square both sides and solve it. So this will be giving us 4h square y square will be equal to m minus 1 by 2 whole square, and we have here lambda square d square plus y square plus z square. So we can just rearrange the terms and we are going to get the equation. This is our 4h square y square minus 1 minus 1 by 2 whole square and lambda square y square minus 1 minus 1 by 2 whole square lambda square z square will be equal to 1 minus 1 by 2 whole square, and this is lambda square and d square. And y square we can take common, so we get this as y square will be equal to 4h square minus 1 minus 1 by 2 whole square lambda square minus 1 minus 1 by 2 whole square lambda square z square is equal to minus 2 whole square lambda square and d square. Now this is nothing but a circle. This is our equation of the circle. So you can say this represents equation of a circle. So therefore the fringes will be of a circular in nature. Fringes will be circular of nature. Now we can find out part B. And part B, we have to find out the ratio of minimum to maximum intensities. And we are given that the 36% of reflected wave is 36% of incident wave intensity. So let us say I1, that is our direct wave, is having a intensity of I. So this is our direct wave. And the reflected wave, let us suppose is I2, and that will be equal to 36%, so 0.36 times I. And this is our direct wave intensity rather. And this we have reflected wave intensity. Wave intensity. And we know that the maximum intensity, max intensity, which is our Imax, is given as square root of I1 plus square root of I2 and its whole square. And we substitute the value. we get this as I1 is our I, so this gives us square root of I plus square root of 0.36 times I and whole square. And we can take square root of I as common. Square root will be coming as this as I, and this comes as 1 plus 0.6, which comes square also, and this comes as 2.56 times I. Similarly, we can say our minimum intensity is our I minimum, and that will be equal to square root of I1 minus square root of I2 and its whole square. Similarly, we can write that our I minimum, that will be coming as 1 minus 0.6 whole square times I, giving us 0.16 times I. So the ratio is our I mean to I max will be equal to 0.16 times I, and this is about 2.56 times I. I goes with I, and this comes as 1 upon 16. And finally, we have to find out for the final part some kind of movement. Minimum distance through which AB should be shifted. Okay, so we can shift this AB, but the intensity at P should again become maximum. So we have part C, and for part C we can divide this into two parts. First is without any movement, and we have a source S, and just behind we have a screen, and that we have point P. This is source S, the height is given as h. So just in front of it we are going to have S prime, that's a virtual, and let us suppose this is our initial condition, and the final condition we can either move, let us suppose this is our AB, we can move this surface towards the, you can say, plus minus x. Okay. So let us move it is somewhere here. So this is our AB, and the object will be, source will be still here, and we can call this as h plus minus x. Similarly, we are going to have our S prime, and this will be also our h plus minus x, and P is still here, and this is our final. We need to find out this x, and so we can say, and it says that intensity, initial condition is that intensity at P is maximum. So for initial condition, intensity at P is maximum. At P is maximum, which is our constructive interference. So therefore, the effective path difference, or we can say that the intensity at P is maximum, therefore the effective path difference difference should be 2h n minus 1 by 2 and multiply by lambda, where n is, you can see, order of the fringe, and lambda 2 is our, because of the phase reversal, because of the reflection. And let us suppose we displace the mirror by x. You can say displace mirror by x. Therefore, it can be displaced upward or downward, doesn't matter. Okay. You can say downwards or upwards. So new virtual image shifts by a distance of 2x. New virtual image shifts by 2x. Okay. Therefore, the new path difference this comes as 2h plus minus x. Okay, it depends upon in which direction the this glass is shifted, upward or downward. So we wrote both plus minus x. So thus we can say that we can divide into two cases. Case 1, mirror is shifted downwards. Mirror is shifted downward, so which basically we can say increasing path length. Increasing path length. Therefore, we can write that 2h plus 2x will be equal to n plus 1 minus 1 by 2, and this comes as lambda, which will be equal to n plus 1 by 2 and multiply by lambda. And case 2, mirror is shifted upward. Mirror is shifted upward. So means decreasing path length. Decreasing path length. Therefore, we can say about 2h minus 2x, this will be giving us n minus 1 minus 1 by 2 and multiply by lambda. This gives us n minus 3 by 2 and this comes as lambda. Now we can solve these two equations for our x. So this is equation number 1 and equation number 2. So from equation 1 and 2, equation 1 and 2, you can say about 2h plus 2x minus 2h is equal to n plus 1 by 2 lambda minus, and here we have one second, I think there is some plus minus 3 by 2. Okay, this is 1 by 2 minus 3 by 2, and this comes as n minus 3 by 2, and this is also multiplied by lambda. So this gives us that 2 of x is equal to, n goes with n with lambda, this comes as 4 by 2. And 1 second, there is some okay, 1 second, my mistake. I wrote equation number wrong. So this is equation number 2, this is equation number 3, and we have just this is our equation number 1. Now it's correct. So we are going to use equation number 1 and 2. Now it is correct. So we get this as n minus 1 by 2 multiplied by lambda. So n and n goes away, so this comes as equal to lambda. Therefore we can say our x is equal to lambda by 2. And if you use equation 3 and first, we are also going to get the same answer, that is x is equal to lambda by 2. You can say from equation 1 and 3, this will be also giving us that our x is equal to lambda by 2. Whether we move upward or downward, the value of x will be equal to same. We already know lambda. So we can say that our x will be equal to 600 nanometer divided by 2. So this gives us that our x will be equal to 300 nanometer. Okay. We go to the next question. It was asked in the year 2003, and it states that a prism of refracting angle 30 is coated with a thin film of transparent material refractive index 2.2 on the face AC of the prism, and a light of wavelength 60-100 angstrom is incident on face AB such that the angle of incident is 60 degree. So based on this, we have two questions. First is find the angle of emergence, and part B, the minimum value of thickness of the coated film on the face AC for which the light emerging from the face has a maximum intensity, given refractive index of material of the prism is square root of 3. So this is given as a figure. So we have a triangular prism, angle is given as 30 degree, incident is, you can say, having an angle of incident at 60 degree, and we have two surfaces. The glass prism is going to have a refractive index of square root of 3, and the face AC, which is coated, is having a refractive index of 2.2. Okay. So first of all, we are going to find out what will be the angle of emergence. For that, we are going to use refraction into the plane at surface AB. So we have part A, and this part A, we consider refraction at AB. And let us draw an approximate figure. This is our AB. This will be a normal, angle of incident is given as 60 degree. And let us suppose it is refracted in this direction. So this will be an angle of refraction. Okay. So here we have a air, and this is our glass, that is a prism. air refractive index 1, prism refractive index is given as square root of 3. So therefore Snell's law at face AB, we can write that refractive index of air sine of I will be equal to refractive index of prism, and this is our sine of R. Air is 1 and in the angle of incidence is given 60, so you can say 1 multiplied by sine of 60. Prism is given as square root of 3 and we have this as sine of R. Therefore from here we get our R refractive angle is our 30 degree. Okay. Now we come to the inside the prism, and we already know the property of the prism, that if this is the prism, so we have a angle of incidence, and let us suppose it moves in this direction and without the coating. So let us suppose this is R1 and this is R2 and this is the angle of prism A. Okay. And we already know that in prism our R1 plus R2 will be equal to the angle of prism, that is our A. Okay. And here this R1 is nothing but our R, so we can say that R1 is equal to R, which is our 30 degree. So we can write that 30 plus R2 is equal to angle of prism is given as 30 degree. So therefore our R2 is equal to 0. So it means if R2 is equal to 0, the ray strikes face AC. So this is our face AC, this is our B. So from here we can say that ray strikes face AC perpendicularly. Okay. So based on this we can write no refraction at the second surface. No refraction at face AC, and it emerges as a straight line because it is perpendicular. It emerges as a straight line. Therefore the angle of emergence will be equal to 0. Therefore angle of emergence will be equal to 0. So more or less we can draw the figure like this, and it bends and it goes. So this is our normal and it comes as perpendicular to the surface. So this angle will be 90 degree and it will be going straight. So this is our A, B and C. So this is our I, and this we considered as R, which was equal to our R1, and this was our R2. So we found out that the angle of emergence is our 0 degree. So this was part first, and we have to find out the minimum thickness of the coated film on the face AC for which the light emerging from the face has a maximum intensity. Okay. And let's draw a so we have a ray, let me draw this according to the surface. So we have two surfaces. One is the prism, which is having a refractive index of square root of 3, and then we have a coating which is having a refractive index of 2.2, and finally it will be coming to the air that is having a refractive index of, let us call this as n1. So inside the prism, this is our n2 inside the thin coating, and this is our n3, that is of air, and equal to 1. And let the thickness of this coating is given as d. Okay. So therefore, as it is going to, the ray is going to strike the coating, and let us suppose this is normal, and it will try to bend in this direction. Okay. And because of the difference in the you can say, because, let me put in words, so this will be partially reflected. So let us call this as ray 1, and here it is our normal, and once again it will be reflected, and we are going to get this, let us suppose, is our ray number 2. So we can say that the reflected ray 1 is reflected from the denser medium, because 2.2 is denser than value 2.2 is greater than square root of 3. So reflected ray 1 is reflected from denser medium, and because of this the phase change of pi will be in the ray 1. So we can say ray 1, there is a phase change of pi, and there is no phase change in the reflected ray 2. We can say that there is no change in the phase for second ray. There is no change in the phase of second reflected ray 2. Okay. Therefore, the condition for maxima for reflected rays, and we can write the formula as this will be equal to 2nd is equal to m plus 1 by 2 and multiply by lambda. And the condition for maxima for the transmitted ray, condition for maxima for transmitted ray and that is given as 2nd should be equal to m times lambda, and we need that the distance should be minimum. So for minimum, value of m should be equal to 1. So we can say for d is equal to d minimum, m should be equal to 1. Therefore, we can write that our thickness of a d will be equal to lambda divided by 2n, that is a refractive index. So n lambda is our 6600, this comes as 2, and the refractive index is given to us as 2.2. Therefore, we can write that this thickness d, this is our d minimum rather, d minimum will be approximately coming as 1500 angstrom. We come to the next question. It was asked in the year 2003, and it states that a ray of light is incident at the glass water interface at angle I. It emerges finally parallel to the surface of water. Then the value of mu g is. Okay. So we have a glass water interface, incident angle of I, and it emerges parallel to the surface of water. Okay. And rest of the parameters are given to us. So we have to find out the, we can say, refractive index, that is mu g. So we can use Snell's law directly, and that will be giving us a solution. So you can say Snell's law at glass water interface. Snell's law at glass water interface. We know that our n1 sine of theta 1 is equal to n2 sine of theta 2. So according to the given figure, we can write this as mu g sine of I is equal to mu w, and this is a sine of r, and mu w is given as 4/3, so this comes as 4/3, and we have this as sine of r. Let us call this equation number 1. And now we apply Snell's law at the air water interface. Snell's law at water air interface. And this gives us, because it says that the light ray emerges parallel. Okay. So here we are given that light ray emerges parallel to the water surface. Water surface. So therefore, angle of refraction will be equal to 90 degree. So therefore, we can write that our sine of r will be equal to 1 upon mu w. And mu w is given to us, so this comes as 3/4. And we can use, let's suppose this is equation number 2. So from equation 1 and 2, from equation 1 and 2, we get our mu g sine of I is equal to this over 4/3 and multiply by 3/4, which comes as 1, because this cancel out entirely. So this gives us that our mu g, refractive index of what you can say glass, will be equal to 1 upon sine of angle of incidence. So the option number B is the correct one. Option B is correct. So we come to the next question. It was asked in the year 2003, and it states that in the adjacent diagram, CP represents a wave front and AO and ABP correspond to rays. Find the condition of theta for constructive interference at P between the rays BP and reflected ray OP. So we are given two rays. One is our AO and another one is our BP. AO is reflected and they are going to meet at point P, and for this point P we are going to find out what will be the constructive interference. Rather than theta, for which we should be getting a constructive interference at point P. And from the figure we can clearly see that this angle will be about 90 degree and this also is 90. So therefore theta, so this angle will be also theta, and we can say this angle is our 90 minus theta. Okay. And the distance is given as between P and the surface is given as D. Therefore we can say that one ray is coming direct to point P and another one is reflected from the surface, and the reflected is going to introduce a path difference. So you can say that ray OP travels a extra distance and that extra distance is our OC. Okay. And this extra distance is nothing but our path difference between two interfering waves. And we can also say that because of the reflection, extra path difference of lambda by 2 between extra path difference of lambda by 2 is introduced between two waves which are interfering. So it means that we for the condition of interference, the total path difference should be integral multiple of lambda by 2. So you can say that total path difference should be an integral multiple of lambda by 2, and we can also calculate the total path difference by using the geometry figure. We can say that total path difference path difference is also equal to our CO plus OP, and these two must be same. So therefore we can say that our CO plus OP should be equal to n lambda by 2. Let us call this equation number 1. And we can express our OP in triangle, we can say OPR. In triangle OPR, our sine of 90 minus theta should be equal to D upon OP. And sine 90 minus theta is our cos theta. So this gives us that our OP will be equal to D upon cos theta. Let us call the equation number 2. And similarly, we can find out the value of our CO. And in that case, we are going to consider triangle COP. So we have in triangle COP, our cos of 2 theta will be equal to CO upon OP. And this gives us that our CO will be equal to OP cos of 2 theta. And we already know our OP, therefore this gives us our D oblique cos theta and multiply by cos of 2 theta. We got our CO and we got our OP. We can substitute it in equation number 1. We can say from equation 1, we can write that our D cos of theta multiply by cos of 2 theta plus D cos of theta is equal to n lambda by 2. And we can use the trigonometric identity to sort it out, and this will be giving us 2D cos of theta is equal to n lambda by 2. And for minimum value of n, which is equal to 1, we can say that our cos of theta is equal to lambda by 4D. And I think this was the only thing which was asked. Yeah. So option number B is the correct one. Option B is correct. Come to the next question, and it was asked in the year 2003, and it states that the size of the image of an object which is at infinity is found by a convex lens of focal length 30 cm is 2 cm. If a concave lens of focal length 20 cm is placed between the convex lens and the image at a distance of 26 cm from the convex lens, calculate the new size of the image. So this we have, you can say, two things. First is we have only the convex lens and we are given the size of the image, and then the concave lens is introduced between the image and the convex lens. Okay, so we can draw the figure. So first we have only convex lens, and so image will be formed somewhere here, and this distance is focal length 20. A size of the image is given. Okay, let us suppose this is our I2. And later on, in the second part, we are given that a concave lens is introduced between the image and the convex. So now we have a concave lens which is something like this. Therefore, so this will be our initial image, which was our I2, but because of this concave, it will try to merge or bend slightly inwards. And let us suppose this is our I1. And it is given that the distance between this is given as 26 centimeters. Okay, so these are the two conditions. So initially the focal length of the convex, let us suppose that is our f1, and image size of convex, let us suppose that is h1. You can see for convex lens, focal length is, let us suppose, f1, which is given as 30 centimeter, and image size let us suppose that is h1, which is given as 2 centimeters. And then we have concave lens, and for concave lens the focal length is, let us suppose, f2, it is will be about 20 centimeter, and obviously with negative sign, and the distance between the two is given as 26. We are given distance between concave and convex lens, convex and concave, let us suppose that is our D, which is given as 26 centimeters. So we can use the standard formula, that is 1 upon F is equal to 1 upon V minus 1 upon U. Okay. So let us find out the image distance from the concave lens. Image distance from concave lens. And the image formed by the convex lens is going to act as an object for the concave lens. Image formed by convex lens will act as an object for concave lens. So therefore our U2 will be equal to our 30 minus 26, giving us 4 centimeter. Now we can use the formula that 1 upon F2 will be equal to 1 upon V2 minus 1 upon U2. And we substitute the values, we get this as minus 1 upon 20 is equal to 1 upon V2 minus 1 upon 4. So this gives us that our V2 will be equal to 5 centimeters. Now we can find out the magnification produced by the concave lens. magnification produced by concave lens and you can say that our H2 will be m times H1, sorry, m2 is equal to m2 times H1. This gives us 5 by 4 times 2. So this gives us that our H2 will be equal to, this comes as 10 by 4. So therefore H2 will be equal to 2.5 centimeters. Okay. Oh, I forgot to find out M2, so let me write it here. Our M2 will be equal to our V2 divided by U2. V2 is our 5 and U2 is our 4. Okay, so this is our M2. So we get that the height H2 will be about 2.5 centimeters, and that is option number B is the correct one. Option B is correct. So this, I think, yeah, so this completes all the 9 questions. So there were 4 questions from the year 2002 and 5 questions from 2003. Thank you.